Alright, I hope I'm live. Is audible. Good morning, everybody. We'll be reading some Geeks for Geeks articles today. Right. We need to complete the algorithms and then, you know, the digital logic and computer organization and architecture. That is what we have planned of doing today. We kind of looked at the divide and conquer. We need to look at the problems of greedy algorithm. In the dynamic landscape of algorithm design, greedy algorithms stand out as powerful tools for solving optimization problems. Aspirants preparing for the GATE exam 2024 are poised to encounter a range of questions that test their understanding of greedy algorithms. These notes aim to provide a concise and insightful overview, unraveling the principles and applications of greedy algorithms that are likely to be scrutinized in the upcoming GATE examination. What is greedy algorithm? Greedy is an algorithmic paradigm that builds up a solution piece by piece, always choosing the next piece that offers the most obvious and immediate benefit. For the problems where choosing locally optimal leads to globally a global solution are the best fit for greedy. Characteristics of greedy algorithm. For a problem to be solved using greedy approach, it must follow a few major characteristics. There is an ordered list of resources, profit, cost, value, etc. Maximum of all these resources, max profit, max value, etc. are taken. For example, in the fractional knapsack problem, the maximum weight value by weight is taken first according to available capacity. Examples of greedy algorithms. Some famous problems that exhibit optimal substructure property and can be solved using greedy approach are job sequencing problem, fractional knapsack problem, Prim's algorithm to find minimum spanning tree, activity selection problem, Dijkstra shortest path algorithm. So this single phrase is going to explain the entire property of greedy algorithms. Advantages of the greedy approach. The greedy approach is easy to implement and typically have less time complexity. Greedy algorithms can produce efficient solutions in many cases, especially when the problem has a substructure that exhibits the greedy choice property. Greedy algorithms are often faster than other optimization algorithms such as dynamic programming or branch and bound because they require less computation and memory. The greedy approach can be applied to a wide range of problems, including problems in computer science, operations research, economics, and other fields. The greedy approach can be used to solve problems in real time, such as scheduling problems or resource allocation problems, because it does not require the solution to be computed in advance. Greedy algorithms can be used in conjunction with other optimization algorithms such as local search or simulated annealing to improve the quality of the solution. Okay. Disadvantages of greedy approach. The local optimal solution may not be globally optimal, may not always be globally optimal. Greedy algorithms do not always guarantee to find the optimal solution and may produce suboptimal solutions in some cases. The greedy approach relies heavily on the problem structure and the choice of criteria used to make the local optimal choice. If the criteria are not chosen carefully, the solution produced may be far from optimal. Greedy algorithms may require a lot of pre-processing to transform the problem into a form that can be solved by the greedy approach. Greedy algorithms may not be applicable to problems where the optimal solution depends on the order in which the inputs are processed. Some of the important greedy algorithms are given below. Activity selection problem. The activity selection problem is an optimization problem used to find the maximum number of activities a person can perform if they can only work on one activity at a time. Problem statement: you are given an activities with their start and finish times. Select the maximum number of activities that can be performed by a single person, assuming that a person can only work on a single activity at a time. Approach: the greedy choice is to always pick the next activity whose finish time is the least among the remaining activities, and the start time is more than or equal to the finish time of the previously selected activity. Hmm. The greedy choice is to always pick the next activity whose finish time is the least among the remaining activities, and the start time is more than or equal to the finish time of the previously selected activity. We can sort the activities according to their finishing time so that we always consider the next activity as a minimum finishing time activity. Okay, that makes sense. But a person can only do one activity at a time. Um, okay. One, two, three, four, five, six, seven, something like that, I guess. Yeah, I guess. Because you can see the differences in color. Maybe if you switch on to the light mode, you will see the difference. These are not all the activities. These little dark gray areas are the selected activities. Alright. N times login, N login. See, why is it N login? Job sequencing problem. The job sequencing problem states that we have a single processor operating system and a set of jobs that have to be completed with a given deadline constraints. Our objective is to maximize the profit given the condition that only one job can be completed at a given time. Given an array of jobs where each job has a deadline and associated profit if the job is finished before the deadline, it is also given that every job takes a single unit of time, so that minimum possible deadline for any job is one task is to maximize the total profit if only one job can be scheduled at a time. Following is maximum profit sequence jobs. See, yeah, alright. Why is it say? We can use the problem using greedy approach. Greedy choose the jobs with maximum profit first by sorting the jobs in the decreasing order of their profit. This would help maximize the total profit as choosing the job with maximum profit for every time slot, so eventually maximize total profit. So if you do that, then first thing will be A, right? And then it should be C, right? And then not after 27. Yeah, D cannot be selected, B cannot be selected, E, right? Is it CAE or ACE? Mm, Is that job sequence uh, No, oh, what? Latest possible free slot before its deadline. Okay, you mean okay, you mean the order of jobs that are placed in the slots. I was thinking of the order in which jobs are being chosen. In that case, it will be ACE because A has the highest profit and the time slot is available, so it must be chosen. Right? Okay, thank you. So, we are thinking of preparing to DSC as well, you know, because it is not some sort of skill that you can earn in a single night. You cannot mug up like a theory subject. Huffman coding. Huffman coding is a lossless data compression algorithm. The idea is to assign variable length codes to input characters, and lengths of the associated codes are based on the frequencies of corresponding characters. The variable length codes are assigned to the input characters as prefix codes means the code's bit sequences are assigned in such a way that the code assigned to one character is not the prefix code assigned to any other character. This is a Hoffman coding made sure that there is no ambiguity when deciding the generated bit stream. Let us understand prefix codes with a counter example. Let there be four characters A, B, C, D, and their corresponding variable length codes are 0001011. This code leads to ambiguity because code assigned to C is the prefix of code assigned to A and B. If the compressed bit stream is 0001, the decompressed output may be triple CD or CCB or A CD or ABS. That is true. There are mainly two major parts in Huffman coding: build a Huffman tree from input characters, traverse the Huffman tree and assign codes to characters. Steps to build Huffman tree. Input is an array of unique characters along with their frequency of occurrences, and output is a Huffman tree. Create a leaf node for each unique character and build a min heap of all leaf nodes. Min heap is used as a priority queue. The value of frequency field is used to compare two nodes in min heap. Initially, the least frequent character is at root. Extract two nodes with the minimum frequency from the min heap. Create a new internal node with a frequency equal to the sum of the two nodes' frequencies. Make the first extracted node as its leaf child and other extracted node as its left child. Add this node to the min heap. Repeat step 2 and 3 until the heap contains only one node. The remaining nodes of the remaining node is the root node and the tree is complete. Create a leaf node for each unique character and build a min heap. Min heap is so wait, let me guess from where does this number come from? Okay, 55. That is divided into. How did it get divided? Uh, yeah. Repeatedly take the two smallest frequencies, merge them, and insert back. Okay, sort by frequency. Merge the smallest. Okay, 5, 9, 14. New list 12 of C, 13 of D, 14 of A, B, 16 of E, 45 of F. Nice. Merge the next two smallest. 12 and 13. 25. CD. Okay. So A, B and E are merged to get 30. Okay. Was it given in that algorithm? Was it given in the proper algorithm definition? I did not understand maybe. Assign 0 to left, 1 to right. Okay. Okay, the Huffman codes are these. I thought these are frequencies. Oh my god. So this is not a second example. So if you took for B 1101. So from B how will you go to root? Okay, 1101. From root to B. From root to C it is 100. So C is 100. Yes it is. Nice. I love this Huffman coding. Create a leaf node. Min heap. Because of min heap, okay. Extract two nodes with minimum frequency from the min heap. Okay. Create a new internal node with frequency equal to the sum of two node frequencies. Okay. Make the first extracted node as its left child and other extracted node as its right child. And this node to the min heap. Nice. This is kind of making sense. Applications, lossless image compression using structures and images, text compression, audio compression. Okay. So I actually need to eat something like tiffin. And is there any way to like stop the video? Guess I need to go to YouTube Studio and check it out. Fractional knapsack, optimal file merge patterns. Okay, nice. Fractional knapsack. All right. Customization. Okay. Analytics. Copyright. Oops. Okay, no idea. No idea how to turn off the cam. But anyways, I will eat and I will come back again. So let's start a timer. I guess 10 minutes is enough. Yep. I hope 10 minutes is enough. Yeah. All right, we're back, people. So let's continue. So before that, I need to ask ChatGPT a question. Right. Oh, the way you explained it was pretty clear and understandable. All right, we will be, implementing this. So this guy told to put a notebook for DSA and all. Design and implementation of a lightweight of large language model. No. Alright. I don't want to sugarcoat it. Is this all good? Yeah, all good. We got like 30 more minutes. And after that, we will take 1 hour of our time solving Python. Basics, learning the basics. They are given a set of items each with weight and value. This is one, right? Yeah, we completed Huffman coding. We are given a set of items each with a weight and value, and we want to find the most valuable subset of items that we can fit into an absolute capacity W. The catch is that we can take fractional amounts of each item, so an item can weigh present in the fractional form. Given the weights and profits of and items in the form of profit weight, put these items in a knapsack of capacity W to get maximum profit. Total profit in knapsack, we are allowed to take fractional values in the knapsack. Input is going to be the array, weight is going to be 50. Output, alright. 10 and 20 gauges, that is 30 already, and fraction of 30 gauges, 2/3 of 30, that is 20. This is 30 and that is 20, total 50, alright. Approach and efficient solution is to use the greedy approach. The basic idea of the greedy approach is to calculate the ratio of profit by weight for each item and sort the item on the basis of this ratio. To then take the item with the largest ratio and add them as much as we can be the whole element or a fraction of it. This will always give the maximum profit because in each step it adds an element so that the maximum possible profit for that much weight. So you need an auxiliary space of O of n here. Optimal file merge pattern is a pattern that relates to the merging of two or more sorted files in a single sorted file. Here we have two sorted files containing n and m records respectively. Then they could be merged together to obtain one sorted file of time O of n plus m. Problem statement: given a n number of sorted files, the task is to find the minimum computations done to reach the optimal file merge pattern. When two or more sorted files are to be merged altogether to form a single file, the minimum computations are done to reach this file are known as optimal merge pattern. If more than two files to be merged, then it can be done in pairs. For example, if needs to merge four files A, B, C, D, first merge A with B to get x1, merge x1 with C to get x2, merge x2 with D to get x3 as the output file. If you have two files of size m and then the total computations will be m plus n. Here we use greedy strategy by merging the two smallest files among the files present. Right. 2, 3, 5, 4, okay, 9, 5. Got it. Node represents a file with a given size, also gives nodes are greater than 2. Add these nodes in a priority queue. Initialize count is equal to 0. Repeat while size of priority queue is greater than 1. Wait plus. Okay. Okay, this algorithm is given and we should be more capable to understand it. Not right now. Prim's algorithm for minimum spanning tree. It is a greedy algorithm that is used to find the MST of a graph. Prim's algorithm finds a subset of edges that includes every vertex of its graph such that the sum of weights of the edges is minimized. Prim's algorithm starts with a single node and explores all the adjacent node with all the connecting edges at each step. The edges with the minimal weight causing no cycles in the graph got selected. Determine arbitrary vertex as starting vertex of MST. Step 2 is to follow step 3 to 5 till there are vertices that are not included in the MST. Find edges connecting any tree vertex with the fringe vertices. Find the minimum among these vertices. Add the chosen vertex to the MST. If it does not form a cycle, return the MST and exit. Time complexity is of V squared. The input graph is represented using an energy sensor list, and the time complexity difference algorithm can be reduced to V log V with the help of a binary heap. In this implementation, we are always considering the spanning tree to start from the root of the graph. Auxiliary spaces of V, okay. Kruskal's minimum spanning tree algorithm. Kruskal's algorithm is a well-known algorithm for finding the minimum spanning tree of a graph. It is a greedy algorithm that makes use of the fact that the edges of minimum spanning tree must form a subset of the edges of any other spanning tree. In Kruskal's algorithm, sort all the edges of the given graph in increasing order. Then it keeps on adding new edges and nodes in the MST. If the newly added edge does not form a cycle, it picks the minimum weighted edge at first and the maximum weighted edge at last. Thus, we can say that it makes locally optimal choice in each step in order to find the optimal solution. Hence, it is a greedy algorithm. How to find MST using Kruskal's algorithm? Below are the steps for finding MST for Kruskal's algorithm. Hey, malapit. Alright. Okay. Below are the steps for finding MST using Kruskal's algorithm. Sort out the edges in decreasing order of their weight. Pick the smallest edge, check if it forms a cycle with the spanning tree formed so far. If the cycle is not formed, include this edge, else discard it. Okay. Ouch. Repeat step 2 until there are V minus edges in the spanning tree. In step 2, we can use union find to detect cycles. Okay. Union find. Most of these are recursive algorithms. Complexity is E log V or E log V. Okay, E log E or E log V. Or V plus E is the auxiliary space where V is the number of vertices and E is the number of edges in the graph. Dijkstra's shortest path algorithm. Dijkstra's algorithm is a popular algorithm for solving many single source shortest path problems having non-negative edge weights in their graphs, i.e. it is to find the shortest distance between two vertices on a graph. It was convinced by Dutch computer scientist Ed W. Dijkstra in 1956. The algorithm maintains a set of visited vertices and a set of unvisited vertices. It starts at the source vertex and iteratively selects the unvisited vertex with the smallest tentative distance from the source. If it then visits the neighbors of the vertex and updates their tentative distances if a shortest path is found, this process continues until the destination vertex is reached or all reachable vertices have been visited. Okay. Need for Dijkstra's algorithm purpose and use cases. The need for Dijkstra's algorithm arises in many applications where finding the shortest path between 2 points is crucial. For example, it can be used in the routing protocols for computer networks and also used by map systems to find the shortest path between a starting point and destination. As explained in How Does Google Maps Work? A star. Alright. Can Dijkstra algorithm on both directed and undirected graphs? Yes, Dijkstra's algorithm can work on both directed graphs and undirected graphs as the algorithm is designed to work on any type of graph as long as it meets the requirements of having non-negative edge weights and being connected. In a directed graph, each edge has a direction indicating the direction of travel between the vertices connected by the edge. In this case, the algorithm follows the direction of the edges when searching for the shortest path. In an undirected graph, the edges have no direction and the algorithm can traverse both forward and backward along the edges when searching for the shortest path. Okay, that is cool. Algorithm for Dijkstra's algorithm. Mark the source vertex with the current distance 0 and the rest with infinity. Select the non-visited vertex with the smallest current distance as the current node. For each neighbor, n of the current node adds to the current distance of the adjacent node with the weight of the edge connecting 0 to 1. If it is smaller than current distance of node, set it as the new current distance of n. Mark the current node visited. Mark the current node 1 as visited. Go to step 2 if there are any nodes. If there are any nodes that are unvisited. Okay. Nice questions, right? So there is a system design. We need to do graph algorithms, dynamic programming, searching, sorting, and technique-based theorem and hashing. Okay. One, two, three. Sure, sure. Okay. So it is not a single scrolling thing. Okay. Okay, it is same like transitive closure. Is it the last one? Let me check. Yes. So you just need to read these two articles. An idea. Dynamic programming, overlapping subproblems, optimal substructure, longest. Where are we? Graph algorithms. A graph is a nonlinear data structure consisting of vertices and edges. The vertices are sometimes also referred to as nodes, and the edges are lines or arcs that connect any two nodes in the graph. More formally, a graph is composed of a set of vertices and a set of edges. The graph is denoted by G, V, E. Representation of a graph. Here are two most common ways to represent a graph. For simplicity, we are going to consider only unweighted graphs in this post. Adjacency matrix, adjacency list. Okay, we need to have a small discussion with ChatGPT before proceeding. All right, 51 minutes. We will. So the idea is very simple. Yep, it should work out. All right. So adjacency matrix and adjacency list. An adjacency matrix is a way of representing a graph as a Boolean matrix, zeros and ones. Let's assume there are n vertices in the graph, so create a 2D matrix having dimensions n times n. If there is an edge from vertex i to j, mark adjacent matrix ij as 1. If there is no edge, mark it as 0, as simple as that. So 1 to 2 there is, and 2 to 0 there is, and so 1 to 2 and 2 to 1 as well. Right, as you can see, this is like a symmetric matrix. We use an adjacency matrix to represent connections between vertices. Initially, the entire matrix is filled with zeros, meaning no edges exist. Alright. Presentation of directed graph as adjacency matrix. Okay. Adjacency list representation. An array of lists is used to store edges between two vertices. The size of array is equal to the number of vertices, that is n. Each index is in this array represents a specific vertex in the graph. The entry at the index I of the array contains a linked list containing the vertices that are adjacent to vertex I. Let's assume there are n vertices in the graph. So create an array of list of size n. Okay, we use an array of lists or vector of lists to represent the graph. The size of the array is equal to the number of vertices here, 3. Each index in the array represents a vertex. Vertex 0 has 2 neighbors, 1 and 2. Vertex 1 has 2 neighbors, 0 and 2. Okay. Appending. Uh-huh. Okay, and I thought of something as well. So, what are the reason cashier and your P and S? Breadth first search for graph-based algorithms for gate exam. Ever wonder how computers figure out the best path in a maze or create efficient networks like a pro? That's where graph-based algorithms come into play. If you are right, I really do wonder if this is a copy-pasted article. So no, I don't think so. A graph is a nonlinear data structure consisting of vertices and edges. The vertices are sometimes also referred to as nodes, and the edges are lines or arcs that connect any two nodes in the graph. More formally, a graph is composed of a set of vertices and a set of edges. A graph is denoted by G of E, comma V. In this comprehensive guide, we will explore the key graph algorithms, providing detailed algorithm steps with its applications, which are relevant for the GATE exam. Okay, I need to go take a break. I'll be back in like 10 minutes. So, see ya. Yes, you can do it. Yeah. Okay. Right. Yeah. We are here again. So breadth first search or BFS of a graph. BFS explores a graph level by level, visiting all neighbors of a node before moving to the next level. It uses a queue data structure to maintain the order in which nodes are visited. Okay. And queue the starting node into the queue. While the queue is not empty, requeue a node and visit it. And queue all unvisited neighbors of the current node. Repeat steps 2 and 3 until the queue is empty. Application shortest path find the shortest path finding in unweighted graphs, connectivity analysis in networks, web crawling and indexing. Depth first search or DFS of a graph. DFS explores a graph by going as deep as possible along one branch before backtracking. It uses a stack or recursion to keep track of the visited nodes. Algorithm steps start at the initial node and mark it as visited. Explore one adjacent node as deeply as possible before backtracking. Repeat step 2 until all paths are explored applications. Now, what is this? Depth first search, right? Yeah. Topological sorting for directed acyclic graphs, detecting cycles in a graph, solving puzzles and games. Detect cycle in a directed graph. Detecting cycles in a directed graph is a common problem with wide-ranging applications in various domains such as network analysis, scheduling, and resource allocation. The algorithmic approach involves traversing a graph using depth first search and identifying packages. If a package is encountered during a traversal, it indicates the presence of a cycle. Algorithm steps initialize arrays for visited vertices and recursion stack start DFS from each unvisited vertex. Mark the current vertex as visited and add it to the recursion stack. For each adjacent vertex, if the vertex is not visited recursively, call DFS. If the vertex is in the recursion stack, a cycle is detected. Okay, recursion stack if the vertex is not visited. Oh god. Remove the current vertex from the recursion stack upon backtracking. My neck muscles kind of ouch. Applications. Task scheduling in project management, resource allocation in computer systems. Topological sort. Topological sort is vital for scheduling tasks and with dependencies and is often used in project management and task scheduling. The algorithm involves linearly ordering the vertices of a directed acyclic graph in such a way that every directed edge UV vertex U come before V in the ordering. Yeah, I kind of read this for solving a gate problem. Start DFS from any unvisited vertex. Mark the current vertex as visited. Recursively call DFS for each adjacent vertex. Add the current vertex to the topological order after recursion. The final order is the reverse of the order in which vertices are added. A task scheduling with dependencies. Is it part of DP? Yeah, we are studying. No, we are studying graph-based algorithms. Okay. Task scheduling with dependencies build systems to determine order of compilation. Okay, I need to get my inhaler, people. Just a second. I'll be back. Bellman-Ford algorithm. The Bellman. Okay, let's see. The Bellman-Ford algorithm is employed for finding the shortest path from a single source vertex to all other vertices in a weighted graph, even if the graph contains negative edge weights. This algorithm is particularly useful in scenarios where Dijkstra's algorithm might fail due to negative weights. Algorithm steps initialize distances from source vertex to all others as infinity, set the distance to the source as zero. Relax edges iteratively. For each edge u, v if distance u plus weight u, v is less than distance v, update distance v, repeat 3 for v minus 1 items where v is the number of vertices, detect negative cycles by checking for further relaxation after v minus 1 iterations. Network routing all protocols. Okay, single source shortest path with negative weight edges. Lloyd Marshall. Oh God. Okay. Floyd-Warshall algorithm is a dynamic programming approach to find the shortest path between all paired vertices in a weighted graph. So we kind of studied for 1 hour, and we will stop it over here, shall we? We'll do something else that is meaningful. 1 hour for DSA. Okay. So according to this guy, lists strings, dictionary, set, stack, queue, sorting, lambda key functions, basic recursion. So we need to fix these. We need to fix these. Let's learn by solving. Give me 3 problems on each topic with increasing difficulty. That works out if I'm not wrong. Open folder, desktop, okay. New folder, Python practice. Selected, alright. Youth core level problems of topics highlights mental brush up my basics like things of layers, person, numbers, details, control. The sound wakes me up at 3 a.m. Can I manipulate less strings comfortably? Okay, so nums is given as list 10, 20, 30, 40. Nums dot right, pen 50, that's a method. Nums dot insert supports index. Okay, 115, I guess. Nums dot remove 30, print nums, yeah. And this, okay. 10, 15, okay. Where I in nums, some plus n equals to nums of I, print some left index out of range. And object must be non-iterable. Ah, okay. So to use for loop in nums iteration for I in nums is not working for I in range nums not do for I when nums not do. Pure basics confusion and expects a number. Iterable. Why? It is an iterable, right? But the sum plus or is equals to nums of I is not working. It is saying out of range. So, what is wrong here? Nonsense already. Okay, okay, that makes sense. Oh god. Okay, alright. We need a lot of basics to be clear, to be honest. Maximum. Oh my god. Ah. How many minutes is it? 125. Wow, it is already 20 minutes. Strings controls. Right. high in range. All right. Come on. You need to access the indices here. Right. String index out of range. Why is okay? Pending. Wow. I mean, mm, Count character frequency. So you will have a dictionary for this? I don't know. Yeah, that, okay. Nice. Frequency of key is equals to value. Frequency of key is equals to value. Nice. Dot get. There is a lot in Python. Oh my god. If key exists, get its value. If not, use 0. Then add 1. Okay. All right. Yeah, this is all right. Good. Let's strings dictionary sets. Stacks. Okay. Queue. Sorting. Lambda. Recursion.